Our solar system contains worlds of staggering diversity, from scorched rocks close to the sun to frozen giants drifting in the outer darkness. Each represents a unique environment, a laboratory of extreme conditions that test the boundaries of what matter and energy can achieve. But viewed through the lens of human survival, these planets share a common trait. They are utterly, spectacularly hostile to life as we know it. The question is not whether you could survive on these worlds without protection, but rather how quickly each one would kill you. The answers reveal just how extraordinary our own planet truly is, and how narrow the margins are that make life possible. Mercury. 2 minutes before the end. Mercury occupies the innermost orbit of our solar system, circling the Sun at an average distance of just 58 million kilometers. This proximity subjects the planet to solar radiation 4.5 to 10.6 times more intense than what Earth receives. The result is a world of temperature, extremes unmatched anywhere else in the solar system. During the day, when the sun hangs directly overhead, surface temperatures soar to 430 degrees Celsius, hot enough to melt lead and tin. The rocks themselves glow with retained heat, radiating infrared energy back into the virtually non-existent atmosphere. But Mercury rotates slowly, taking 59 Earth days to complete a single spin. This leisurely rotation, combined with the planet's complete lack of atmosphere, means heat cannot be retained or distributed. When night falls, temperatures plummet catastrophically to minus 180 degrees Celsius. The swing between day and night temperatures exceeds 600 degrees, the most extreme variation of any planet. No atmosphere means no greenhouse effect, no heat retention, no moderation whatsoever. The surface temperature is determined entirely by whether that patch of ground faces the sun or the void. If you were somehow transported to Mercury's surface without a spacesuit, your survival time would be measured in seconds rather than minutes. On the day side, you would face immediate threats from multiple directions. The intense solar radiation would begin cooking exposed skin instantly. Within 30 seconds, severe radiation burns would cover your body. The heat would be so extreme that your sweat would flash into steam before it could cool you. Your blood would literally begin to boil, not from the heat alone, but from the near total absence of atmospheric pressure. Mercury's surface pressure measures less than 1/1,000,000th that of Earth's atmosphere. This is effectively a vacuum. In such conditions, the liquids in your body would boil at room temperature, a phenomenon that occurs whenever pressure drops below the Armstrong limit of 6.3 kilopascals. The fluids wetting your lungs, the saliva on your tongue, the tears in your eyes would all begin to vaporize. The dissolved gases in your bloodstream would come out of solution, forming bubbles that would expand and cause extreme pain, as they blocked blood vessels. You would not explode, despite what science fiction might suggest, but you would certainly feel as though you were being torn apart from the inside. Asphyxiation would race against radiation poisoning and thermal trauma to determine cause of death. Without air to breathe, you would lose consciousness within 15 seconds as oxygen-starved brain cells began dying. Cardiac arrest would follow shortly after. From touchdown to death, perhaps 2 minutes would elapse on the day side of Mercury, and that is being generous. On the night side, you might last fractionally longer, perhaps another 30 seconds, as extreme cold rather than extreme heat became the primary killer. Either way, Mercury offers no mercy to unprotected human tissue. Venus. Seconds in hell. Venus represents perhaps the most hostile environment in the inner solar system, a world where every parameter seems designed to extinguish life. Often called Earth's twin due to similar size and composition, Venus instead serves as a cautionary tale of runaway greenhouse effects and atmospheric evolution gone catastrophically wrong. The planet's atmosphere consists of 96% carbon dioxide, with clouds composed almost entirely of sulfuric acid. These clouds reflect about 75% of incoming sunlight, giving Venus the highest albedo of any planet. But what little solar energy does penetrate is trapped by that massive blanket of greenhouse gases, creating surface conditions that dwarf Mercury's worst extremes. The surface temperature on Venus holds steady at 464 degrees Celsius, hot enough to melt lead, zinc, and certain types of glass. This temperature remains constant whether you stand on the day side or the night side at the equator or the poles. The thick atmosphere distributes heat so efficiently that temperature variations are negligible. More terrifying still is the atmospheric pressure, 92 times that of Earth's surface, equivalent to being nearly 1 kilometer underwater in Earth's oceans. This pressure is sufficient to crush most spacecraft that have attempted to land on Venus. The Soviet Venera landers that successfully touched down in the 1970s and 1980s survived for mere hours before being destroyed by the combination of heat and pressure. If an unprotected human appeared on Venus's surface, death would be nearly instantaneous. The atmospheric pressure alone would be immediately lethal. Your rib cage would compress, your lungs would be unable to expand, your organs would be squeezed by forces your body has no defense against. But you would not live long enough to dwell on the pressure. The extreme heat would flash vaporize any exposed moisture. Your eyes would desiccate and cook in their sockets within a fraction of a second. Your skin would blister and char. The air you tried desperately to inhale would consist of carbon dioxide and traces of sulfuric acid vapor, which would sear your respiratory tract even as the heat cooked it from the outside. Estimates suggest that an unprotected human on Venus would survive less than 1 second. You would not have time to take a breath, to feel pain, or to understand what was happening. The hostile environment would simply erase you, reducing human tissue to charred carbon in the blink of an eye. Venus demonstrates that planetary conditions can create environments so extreme that survival time approaches zero, where death is not a process but an instantaneous event. Mars. 2 minutes of consciousness. Mars has captured human imagination for over a century as the most potentially habitable world beyond Earth. Its rusty red surface, its polar ice caps, its ancient riverbeds all suggest a planet that was once more welcoming than it is today. But modern Mars is a cold, dry desert with an atmosphere thinner than the air at the summit of Mount Everest. The average surface temperature hovers around minus 63 degrees Celsius, though it can range from a relatively balmy 20 degrees Celsius at the equator during summer afternoons to a bone-chilling minus 153 degrees Celsius at the winter poles. The atmospheric pressure on Mars averages just 600 pascals, roughly 0.6% of Earth's sea level pressure. This puts Mars well below the Armstrong limit, where water boils at body temperature. The atmosphere consists of 95% carbon dioxide, 2.7% nitrogen, 1.6% argon, and only trace amounts of oxygen. You cannot breathe Martian air. Even if it contained breathable oxygen, the pressure is so low that your lungs could not extract it efficiently. You would suffocate just as surely as if submerged underwater. If you stepped onto the Martian surface without a spacesuit, several things would happen simultaneously. The low pressure would cause the water in your body to begin vaporizing. Exposed surfaces of your eyes, tongue, and respiratory tract would boil. The dissolved gases in your blood would form bubbles, though not as dramatically as on Mercury due to slightly higher pressure. You would feel your body swelling slightly as the gases in your tissues expanded. Your skin provides some structural integrity, so you would not rupture, but the sensation would be deeply uncomfortable. More immediately threatening would be asphyxiation. The moment you tried to breathe, you would inhale air with no usable oxygen. Your body would immediately recognize this and trigger panic responses. You would gasp desperately, trying to find oxygen that simply does not exist in Martian air. Brain cells require oxygen to function. When deprived, they begin dying within seconds. You would lose consciousness in about 15 seconds. Your heart would continue beating for perhaps another minute before cardiac arrest, but you would be unaware of this. Total survival time from exposure to death would be roughly 2 minutes, with consciousness lasting only a fraction of that. The cold would not kill you immediately, though it would certainly contribute to your demise. If by some miracle you were not killed by the low pressure and lack of oxygen, hypothermia would finish the job within 15 to 30 minutes. But this scenario is academic. The atmospheric conditions are lethal long before temperature becomes the primary concern. Mars demonstrates that a planet can appear tantalizingly Earth-like from orbit while remaining utterly inhospitable at ground level. Jupiter. Instant obliteration. Jupiter exists in a fundamentally different category from the inner rocky planets. As a gas giant, it possesses no solid surface to stand upon. The planet consists almost entirely of hydrogen and helium gas, with clouds of ammonia, water, and various hydrocarbons floating in thick atmospheric layers. What we see when we observe Jupiter through telescopes is merely the upper cloud deck, a tempestuous zone where wind speeds exceed 400 kilometers per hour and storms larger than Earth persist for centuries. If you attempted to approach Jupiter, you would die long before reaching what might generously be called its surface. At a distance of approximately 300,000 kilometers from Jupiter's cloud tops, about 2.5 times the distance between Earth and the Moon, radiation would become lethal. Jupiter possesses a magnetic field 20,000 times stronger than Earth's, and this field traps charged particles from the solar wind, creating radiation belts far more intense than the Van Allen belts surrounding our planet. The radiation in these zones is so severe that it fried electronics on the Galileo probe, and no human could survive exposure even inside a conventional spacecraft. But let us imagine you possessed perfect radiation shielding and were somehow deposited into Jupiter's upper atmosphere, where pressure equals 1 bar, similar to Earth's surface. You would not find yourself standing on anything. You would be falling, accelerating through thickening layers of hydrogen and helium gas. The temperature at this level hovers near 0 degrees Celsius, cold, but not immediately, fatal. For a few seconds, you might even feel strangely peaceful, floating through dim amber clouds with lightning storms flickering in the distance. But you would be descending rapidly into a hell far worse than anything Venus offers. As you fell, pressure would increase exponentially. Within a minute, you would reach depths where pressure exceeds 10 Earth atmospheres and temperatures climb above the boiling point of water. Your body would be unable to withstand the crushing forces. Your ribcage would collapse, your organs would be compressed, your skull would fracture. But even crushed, your remains would continue falling. Deeper still, at pressures measuring thousands of Earth atmospheres and temperatures soaring into thousands of degrees, the hydrogen around you would no longer behave as a gas. It would transition to a liquid, then to a bizarre state called metallic hydrogen, where the atoms are packed so tightly that electrons break free and flow like a metal. At Jupiter's core, temperatures may reach 24,000 degrees Celsius, hotter than the surface of the Sun, and pressures measure millions of times Earth's surface pressure. Any trace of what had been you would be atomized, broken down to constituent elements, and scattered through the planet's turbulent interior. From initial exposure to complete molecular destruction, less than 1 second of survivable conditions before obliteration. Saturn, Uranus, and Neptune. Variations on annihilation. The remaining gas and ice giants of our outer solar system present similar challenges to Jupiter, each with unique atmospheric quirks that make them equally lethal. Saturn, famous for its majestic ring system, features winds that can exceed 1,800 kilometers per hour at the equator. Its atmospheric temperature at the 1 bar pressure level measures minus 140 degrees Celsius. Like Jupiter, Saturn lacks a solid surface, and any attempt to enter its atmosphere would result in steadily increasing pressure and temperature until your body was crushed and vaporized. The core temperature of Saturn reaches approximately 11,700 degrees Celsius, and pressures there would dwarf anything Jupiter offers. Uranus holds the distinction of being the coldest planet in our solar system, despite not being the most distant from the Sun. Its upper atmosphere drops to minus 224 degrees Celsius, colder than Neptune, despite being closer to our star. This occurs because Uranus possesses essentially no internal heat source, while Jupiter, Saturn, and Neptune all radiate more energy than they receive from the Sun. Uranus does not. Its core temperature measures only about 4,627 degrees Celsius, roughly 1/5 of Jupiter's core heat. This makes the upper atmosphere remarkably cold and stable, with few dramatic weather features. But the cold would be the least of your problems if deposited into Uranus's atmosphere. The pressure would crush you within seconds, just as it would at any gas giant. The atmosphere consists primarily of hydrogen and helium with significant amounts of methane, which gives Uranus its distinctive blue-green color. Winds at the equator can reach 560 kilometers per hour, and these would tear apart any unprotected human body. The survival time would be identical to Jupiter, less than 1 second before the combination of pressure, cold, and atmospheric violence destroyed you completely. Neptune, the most distant major planet, features the most extreme winds in the solar system. Near its equator, jet streams reach velocities of 2,100 kilometers per hour, approaching supersonic speeds relative to the atmosphere's sound speed. These winds drive storm systems larger than Earth itself. The Great Dark Spot observed by Voyager 2 in 1989 measured roughly the same size as our entire planet. Neptune's upper atmosphere temperature hovers around -200 degrees Celsius, though, like all gas giants, temperature increases dramatically with depth. Neptune's internal heat source is substantial, actually, radiating more than twice the energy it receives from the Sun, despite being 30 times farther from our star than Earth is. This internal heat drives vigorous convection and contributes to the planet's extreme weather. But once again, this makes no practical difference for human survival. Drop an unprotected human into Neptune's atmosphere, and the outcome would be identical to Jupiter, Saturn, or Uranus. Immediate death from crushing pressure, followed by vaporization deeper in the atmosphere. The outer planets are not merely hostile to human life. They are incomprehensibly alien environments where the very concept of survival has no meaning. The precious exception. When we survey the planets of our solar system through the lens of human survival, a pattern emerges with stark clarity. Mercury offers perhaps 2 minutes before death. Venus grants less than 1 second. Mars provides 2 minutes, though consciousness lasts only 15 seconds. The gas and ice giants allow no survival time whatsoever, killing instantly through pressure and temperature extremes that exceed anything the inner planets can produce. Only Earth, our fragile blue world, offers conditions where humans can exist without technological protection. Earth's atmosphere provides breathable oxygen at precisely the right pressure. Temperatures, while varying considerably across the globe, remain within the narrow range where water can exist as a liquid. Our magnetic field shields us from solar radiation and charged particles. Our ozone layer filters out harmful ultraviolet light. The gravitational pull is strong enough to retain our atmosphere, but not so strong that it crushes life. Every parameter required for human survival falls within an incredibly narrow range, and Earth maintains all of them simultaneously. This is not an accident of chance. Life shaped Earth's atmosphere over billions of years, converting the carbon dioxide-rich primordial air into the oxygen-rich envelope we breathe today. Liquid water carved the continents and continues to moderate our climate. Plate tectonics recycles carbon and maintains conditions suitable for life. Earth is not merely a planet that happens to support life. It is a planet that has been transformed by life, creating and maintaining the very conditions necessary for that life to persist. The exploration of how long humans could survive on other planets reveals a profound truth. We are children of Earth, adapted through millions of years of evolution to this specific world's conditions. Remove us from Earth's protection, and we become fragile biological machines rapidly overwhelmed by hostile physics. The journey from Earth to any other planet in our solar system is not merely a voyage through space. It is a transition from the one environment in the solar system where human life makes sense to environments where it cannot possibly exist. In the entire solar system, spanning billions of cubic kilometers of space and 8 major planets, only one thin shell of atmosphere on one world offers refuge for creatures like us. That should inspire both wonder at our good fortune and determination to protect the world that protects us. If this exploration of planetary survival has given you a new appreciation for the uniqueness of Earth, make sure to subscribe for more deep dives into the science that shapes our universe. We live on a world that is, as far as we can tell, utterly exceptional in our cosmic neighborhood, and understanding why should remind us how precious and irreplaceable our home truly is.